All right, thank you for the introduction, Zara. And so my talk today is about a new communication technique that we devised in my lab a few years ago, and we have been pursuing since. It has multiple use cases in both civilian and defense applications. And this is joint work with several of my students. Particularly, I'd like to mention Paris Karakassis, Ibrahim Salah, and Spiros Pepas. And let's get right to it. So the motivation for this work is that, as you all know, there is an ever-increasing demand for more and more spectrum, and this pushes us to higher frequencies. But on the other hand, low and mid frequencies are very valuable because they have much better propagation characteristics, far less attenuation than higher frequencies. At the same time, because the existing spectrum, especially the lower and mid bands, have already been allocated to a large extent, there is less and less spectrum available for exclusive use. So this has driven a paradigm shift in wireless communications. The spectrum sharing paradigm emerged some 20, 25 years ago, and the idea being that if you can more effectively share spectrum, you can have much better overall utilization of the available spectrum. So there's been more than 20 years of research on what is known as dynamic spectrum access, cognitive radio, secondary underlay, which is one particular way of doing cognitive radio. But no practical system except CBRS has ever adopted these techniques. And CBRS, which is a spectrum reuse, let's say, band, right, is not really dynamic and it does not support underlay. So this has been the state of affairs in this area until a couple of years ago. And then back in 2022, together with my student Salah Ibrahim and Paris Karakassis, we came up with a very simple and practical scheme for underlay communications, for short-range underlay communications. And I would like to tell you a little bit about this, the idea in this paper, the basic idea in this paper, and then build upon it. So the idea builds on something that is very simple, and you only see it after the fact, once you know a certain mathematical statistical technique known as canonical correlation analysis, and then you reverse engineer what you need to do at the transmitter. So the basic idea builds on repetition coding at the transmitter and using two or more receive antennas at the receiver. And the idea is quite simple, and I can explain it using the graphic on the top of my screen. So you have a receiver with two receive antennas, what you see here on the very left, right? And you have a primary transmitter, let's say a radio station that is transmitting whatever it wants to transmit. The blue signal here, P1 transposed, is the signal of the FM station that is playing. The orange signal below it is the secondary signal that you want to transmit over a short distance, right? In the same band at the same time as the FM or other, let's say, legacy service that is using that part of the spectrum. Now, because of superposition of electromagnetic waves in the air, what your first antenna receives is a linear combination of the FM, let's say, signal or whatever it is that the primary transmitter is transmitting, and the secondary, the orange transmission that you are transmitting, right? So it is a linear combination of these two, which is modeled as a 2x1 or a 1x2, let's say, vector, right? In the first row of this matrix, say it's 1, right? Which combines these two signals. And that is what you receive from the first antenna. On the second antenna, you receive a different linear combination of the same two signals, right? The primary transmission and the secondary transmission in orange. So the key idea, so what you receive is basically a 2 by n matrix here. N is the length of the signals in time domain, right? 2 is the number of antennas. You may have more than 2, but we assume at least 2, right? At the secondary receiver. Now, the key trick here is that the secondary transmitter sends this orange signal and then repeats it again, perhaps in a back-to-back fashion, right, immediately afterwards. Now, what happens is that the primary transmitter, in the meantime, is transmitting a different signal. We will call it P2 transposed, but you, the secondary transmitter, are simply repeating the previous transmission. So for every packet, let's say, that you wish to transmit, you send it twice. That's repetition coding. Now, if you take a look at this picture, you will realize that what you have as data here is two matrices, two 2 by n matrices, which I can transpose and make them n by 2, right, for reasons of notational convenience. And these two matrices, right, have a certain span, right? Every one of them spans a certain subspace of n-dimensional space. So this matrix, for example, the columns of this matrix live in the space spanned by S transpose and P1 by S and P1, if you transpose things. This one in the space spanned by S and P2. So there is a key property for this pair of matrices that with probability 1, right, unless P2 is the same as P1, right, or proportional to P1, in fact, right, which will not happen. I will explain why. These two matrices share a common one-dimensional subspace, and this common one-dimensional subspace is the orange signal, right, or what is spanned, right, by this orange signal, right. The key for this to work is to have effective means of computing the intersection of two subspaces, which we do. And the tool that does this is known as canonical correlation analysis, as we have shown a few years ago. So if we can do in a computationally efficient manner canonical correlation analysis, which is for our purposes tantamount to subspace intersection, we can recover the orange signal guaranteed, no matter how much stronger the primary signal is. So that's the sort of the key message here, right? And mathematically, it is written down here. So I transpose these two matrices from fat, I make them tall in the transposed version. So each one of them is a linear combination of two n by 1 vectors, the orange vector, right? And this V1 here, V1 plays the role of P1 there, right? And we can recover the orange signal by subspace intersection through what is known as canonical correlation analysis. There is mathematical proof that you can do this, and the algorithm is quite simple. It's not complicated at all. It amounts to a principal component computation of a sort matrix. So I will leave the details for later if you are interested. Now, I've been known as a theorist and someone who develops methods for most of my life, but this one is practical enough to actually implement and test in the lab, and that is what we did a couple of years ago. So what you see here is my lab at the University of Virginia, and we are actually, we set up a prototype to implement this kind of setting. So what you see here, there is a primary transmitter and a primary receiver, and then there is a secondary transmitter and a secondary receiver. The secondary receiver has two antennas. Every one of these transmitters here or receivers is a software radio that we have in the lab, and we can program to set up a prototype of this situation and measure it in practice. And so here are the parameters of our prototype. The carrier frequency that we used was 1.2 gigahertz, 100 kilohertz bandwidth, 1 megasample per second sampling rate, 12 bits analog to digital conversion per in-phase and quadrature channel, and some other details. I will not spend too much time on those. It's important to note that what we do is we have a primary that transmits, so the primary link transmits at 20 dBm, so it's 20 milliwatts, right? And the secondary link transmits at far lower power than the primary link. So it transmits between -20 and -10 dBm. So the transmit power difference is from -40 dB to -30 dB, right? So much lower, right? The modulation for both is QPSK, and these are the distances in meters, which you can sort of assess from the picture as well. Just to give you an idea of the power imbalance between the two links, here is the spectrum. What you see here in the blue line down here is the background noise, AWGN. There is a little bit of leakage in this software radius. That's why you see a little bit more power spectral density in the low frequencies. That's because of the leakage. Above it in purple is the secondary spectrum, the secondary transmission spectrum. So you see it is around -80 dB, right, at the receiver side. And the red is the primary, which is -40 dB, right? So you see the power difference. This is for transmission power, -20 dBm, right? So there's tremendous power difference between primary and secondary, which makes it normally very, very, very hard to decode the secondary, right? That's another illustration of the same thing, but I will, in fact, the two are not perfectly aligned in time, so the primary transmits with significant but not complete overlap, right? So we wanted to compare our idea to what is possible with earlier methods. And so the question is, what are the baselines here? Because we assume no channel state information, no coordination, nothing between the primary and the secondary system. They are completely autonomous. So one baseline that is kind of obvious is to use a singular value decomposition, because you know that the primary signal is much stronger. You can use singular value decomposition to estimate the direction, let's say, or the spatial channel of the primary transmitter, and then project on its orthogonal complement, which hopefully contains the secondary signal. But that is not working very well because the power difference between the two systems is fluctuating due to fading, even in the lab, and that mixes essentially the two one-dimensional subspaces, and therefore what you get out of singular value decomposition actually cancels the secondary signal as well, right? The other is to assume an ideal baseline, an oracle, a genie, that will know the exact secondary channel when it can possibly estimate that when the primary user is inactive, if it is inactive and it knows that it is inactive, and then basically do maximal ratio combining or spatial match filtering to decode the secondary signal, but without any interference from the primary user. So that's a genie or oracle, because we magically remove the primary and we do the best thing possible for the secondary, right? So clearly nothing can beat this very optimistic baseline, right? So these are real experiments in our lab. This is no simulation. And what you see is the symbol error rate of the secondary user as a function of the average secondary signal to noise ratio in dB for a fixed primary interference power at 10 dBm. So they have a roughly 30 dB SINR, right? So what you see here is the ideal, the oracle, the genie performance if there were no primary, right? But there is actually at 30 dB. That's the ideal performance. This is what we get using our canonical correlation analysis method. This is what the SVD with interference does. It misses it almost altogether, right? So the thing works very well in practice. I will not, I don't want to, spend too much time on details, but it works very well in practice. Now, if you are a communications engineer, you know that the toughest problem in this context, especially when you are trying to decode a signal that is, 30, 40 dB below the primary, let's say, interference, the Achilles heel of any communication system in this regime is synchronization. How can you do it when you're really buried under the primary interferer? And it turns out beautifully and fortuitously that you can exploit the same repetition structure that we use, right, to decode the common subspace. You can exploit that very same repetition structure, solve a series of canonical correlation problems, and that essentially tells you what is the right timing, right? So it allows you to do timing synchronization in this very challenging regime. It works even when the power difference is 40 dB, which would otherwise require, you know, hundreds of thousands of symbols for synchronization, right? So that's really nice. So let me summarize the take-home points. The take-home points is that simple repetition coding with appropriate processing at the receiver, canonical correlation analysis for subspace intersection, offers seamless short-range reutilization or reuse of the channel at half rate because of the repetition for free. And we know no other way of communicating in this regime effectively, right? It doubles as an effective synchronization strategy, even at extremely low SINR levels, where the Achilles heel of the system is synchronization. It is also immune to CFO due to a beautiful shift property of complex exponential, which I didn't have time to explain, but you can correct the carrier frequency offset after extracting the secondary signal. And it works in practice remarkably well, in my opinion, one of the very few cases where theory actually predicts laboratory experiments so well. It is worth noting that this works without requiring any channel estimation, not even the secondary transmitter, secondary receiver. You don't even need that channel. The channels can change from one packet transition to the next. That is perfectly fine. It works with primary and secondary signals that are digital modulated or analog modulated. You can add a lot of bells and whistles, for example, a pseudo-random interleaver to the secondary for protection and to make sure that even if the primary is trying to repeat frequency hopping for the repetition, you can hide under 2 TV stations, which makes it harder for others to detect your transmission. And you can, of course, randomize the repetition timing as well. So there's a lot of options here that have a lot of interesting applications. So in theory, this works even when the signal to interference plus noise ratio is, you know, below -40 dB. But in practice, the limitation, the practical limitation is the resolution of your analog to digital converter and linearity of your receiver front end. So there is a physical limitation. We are using 12-bit, relatively cheap analog to digital converters, which we have in our software radios, and that allows us to go down to -40 dB, so that's already very good. Now, I call this technique, I named it signal alignment, because what you do is you align the signal, right, through repetition in this particular case. And I'd like to compare it to something that is quite well known in the wireless communication community, known as interference alignment. So interference alignment, what you're trying to do is to somehow instruct your interferers to contain themselves in a subspace of the full space, which will give you, the secondary, let's say, communicator, room, right, for interference-free communication. So there will be an orthogonal subspace to the interference subspace where your communication transmitter can signal, right? However, that requires a lot of channel estimation, coordination, back and forth, and it requires that the channels remain time invariant. And that is not practical, right? So although theoretically elegant, interference alignment has not been implemented in practice for these reasons. But signal alignment, when you are trying to align the signal, right, you are free from all this channel state information exchange, control, instructing others how to transmit, right? So there's no coordination here because you align the secondary signal, not the interference. So that's a big difference. I promised to talk about use cases of this technology. And so let me give you a few. One obvious thing is Wi-Fi in congested areas. Let's say you are in a Manhattan skyscraper and all the Wi-Fi channels are essentially occupied. So you have a back room and your neighbor's Wi-Fi is stronger than your Wi-Fi. How can you communicate, right, in that room? So you can use this technique to do that. IoT communications, as you know, there are now IoT, Internet of Things, sensors deployed all over the world at very, very rapid pace. And these use protocols known as Sigfox and LoRa for data collection, right? And these protocols actually have built-in repetition for improved reliability relative to fading. So Sigfox, for example, transmits every packet 3 times in 3 different hop frequencies for better immunity. Well, with signal alignment, we can actually use those repetitions to improve performance and resist interference from a primary signal, which will allow us essentially to reuse existing good low frequency and mid frequency bands, right, to do data collection in IoT with much better performance. Another application is emergency communication. So suppose that there is an emergency and the government wants to reuse the allocated FM frequency stations to broadcast an emergency message, right? How can you do that without really interfering with, or without having to tell the FM transmitters, stop transmitting, the government now wants to transmit an important message, right? You don't have to with the signal alignment technology. Finally, there are important applications in defense. In particular, think of the FM transmitter or the primary transmitter as being a jammer that is trying to deny your ability to communicate. You can use this technology to withstand that. You can also use it to transmit inconspicuously under legitimate high power stations. All right, so which brings me to what we did with CCI support. We received this year a small translation commercialization grant from CCI, and we used that to do laboratory deployment and experimentation. And the problem, we looked at 2 problems. The one that took most of our time, I will talk about now. And this has to do with pushing the envelope further and operating our technique, so doing a demonstration under a commercial FM station. Because the previous lab work we did, we actually instantiated the primary transmitter using another pair of software radios, but that is not very realistic. So the question we asked ourselves is, how can we demonstrate actual underlay transmission under a real commercial FM station, right? And can we really do it under a broadcast FM station, which is, transmitting maybe at kilowatts, despite the very strong and time-varying interference from the FM station. Now, there are, relative to what we did earlier, even though I mentioned that the repetition idea and canonical correlation analysis works with analog modulations, FM is not only analog, it is a non-linear modulation, and it has memory, which makes it technically interesting. So the answer is yes, and I will show you a demo of this. It does work, and you will hear it work. But beyond, maybe I should say a few words of why we wanted to do this. One reason is because it is a realistic demo. The other is that if you can demonstrate this with FM transmitters are cheap and very low power consumption compared to digital circuitry. And also you can actually hide under a conventional FM broadcast. Another reason, last but not least, as I would say, is that this is a fun project to do, and it sort of reconnected me to my motivation for becoming an electrical engineer, which was, well, 45 years ago, or a bit more than 45 years ago, I became a radio enthusiast, and I was building FM stations at the time. And so it's always good to go back and sort of tweak an FM transmitter and receiver to do what we want it to do. So let's see how this works. So for FM, you start with an audio waveform, which you can sample if you want, but in analog FM you don't. So so you have the MT directly, and then you essentially frequency modulate. And what does this mean? You take the audio waveform or the speech waveform, you integrate it as shown here from 0 to T, right? So that's your entire speech history that you integrate, right? And you use that as a phase in a complex exponential, right? So so you add that in a complex exponential. That's a carrier frequency. And because there is no complex number transmission in practice, you take the real part of that. So what you are actually transmitting is cosine, right? 2 pi FCT plus that integral m tau d tau, right? So although we don't have to use repetition, we can do this in another way, as I will tell you a little bit later. We can do repetition here, so we can take small segments of my speech, let's say 50 milliseconds of my speech, right, and repeat them. So what we do is we repeat the samples and we create the repeated waveform, and we use that to modulate. So M tilde is my speech signal, right, or my student's speech signal, as you will hear, that is sampled, repeated, right, and reconstituted in an analog waveform, right? Now, because of this repetition, if you look, segments of which, right, are repeated, not the entire thing. So if you look at the repeated segment, right, the modulated signal can be written in this form. So you have this real part of this complex exponential, and you have M tilde here, but M tilde is has this repetition structure. So you can write it as integral from 0 to T naught, and then T naught to T, right? T naught is the first transmission. And then basically, right, what you end up with because of the repetition is this, right? So following down conversion, we basically multiply with a carrier, right? Following down conversion, the baseband equivalent model is this. So you have exponential to the j2 pi integral 0 to t m tilde tau d tau. And there you have a theta, and the theta is due, right? The theta is due to the integral from 0 to t naught m tilde of tau, right? So this part, exponential to j2 pi, this part is this theta, right? 2 pi times this part is this theta, right? So if you take a look at the baseband signal representation, right, the real part of this, couple of important things to note. First of all, is you cannot use canonical correlation analysis after demodulation. The reason is that you linearly add, right, the primary and secondary signals before demodulation, but FM demodulation is a nonlinear operation. So after FM demodulation, you will not have superposition, right? And in fact, you are all familiar with this. If you are driving your car in the countryside and you're listening to an FM station, right? You will hear sometimes interference from another FM station, right? But even though they are transmitting at the same frequency, most of the time you only hear one of them, the strongest one. That is because of the capture effect. So the FM demodulator locks, right, on the stronger of the two signals, right? So in our context, the FM demodulator will lock on the primary FM signal and completely obliterate or ignore your secondary transmission, right? So we cannot use CCA after demodulation. Turns out that we cannot use it before demodulation either, because of this theta here. If I take the real part of this, it's going to be a cosine theta plus, right, which is not the same as what you have in the first part of the transmission because of this theta, right? Because FM has memory. So we cannot use CCA before demodulation either if we take the real part of this. So that it sort of posed a challenge for a moment, but soon after we realized that what we can do, right, is work with a complex analytic signal, right? So if you use the Hilbert transform, let me take you back to your signals and systems days. You use the Hilbert transform, right, which basically is a filter that is 0 for all negative frequencies and 1 for all positive frequencies, or an approximation of that filter. When you use a Hilbert transform, you take a cosine, right, and you map it to a complex exponential, basically, right? You map it to a complex exponential. So you use the Hilbert transform, then you work with a complex Bayesian representation, and there, the second transmission and the first transmission differ by a complex multiplicative constant. They are proportional as complex signals, and this allows the use of CCA. So this is an example showing how this works for synchronization. So what you see here is how the secondary FM receiver uses the repetition structure to find the proper timing of the secondary transmission, even though it is 30 dB below the FM broadcast, right? So much, much weaker. A regular FM receiver cannot detect this signal, right? But our CCA receiver can detect, synchronize, and decode. And what I'm showing you here is real lab measurements. This is a piece on the right, is a piece of the speech of my student, which you will hear shortly, right? This is the transmitted speech, and this is the recovered speech using actual hardware, the software radios in our lab, and our demodulation strategy, right? So the correlation coefficient between the two is 0.98, relative root mean squared error is minus 15 dB, so there's very good agreement between the transmitted analog speech and the received speech after CCA demodulation, even though the received secondary signal is 30 dB or less than 30 dB below the broadcast FM transmitter. So before I go on, let me play out a video so that you can hear and see this. So this is my student Nima Razavi, who worked with AI last summer.
Okay. So I'm going to start the reception first, and then I'm going to turn on the transmitter.
Mm-hmm. What here is 97.5. Let's go.
Now we'll do we will find the secondary and do processing on MATLAB. Aha, found it.
Hello, this is Nikolaos Sidiropoulos, an electrical engineering student. 1, 2, 3, 1, 2, 3.
That was very good. All right. So that was Nima doing the demonstration. All right. So what are the take-home points for this part of the presentation? To the best of my knowledge, our work with support from CCI this past spring and summer marks the first real-life demonstration in real time, actually, of underlay transmission under a powerful FM station in the lab, right? Without any coordination or channel state information, with built-in means of synchronizing with a secondary FM transmission, even though it is buried under the primary FM station, right? More than 30 dB power difference between the two. Synchronization is the toughest problem, and we are not disturbing the reception of the commercial FM station, right? So we could actually listen, you listened to the commercial FM broadcast at the same time as the secondary was transmitting. There is no way to tell a difference. Part of this is because we are transmitting at very low power, right? The secondary transmission is at very low power. Part of this is due to the natural capture effect in normal FM demodulation. It locks onto the stronger of the two FM signals, therefore further suppressing, right, the secondary. And even within the lab, right, there is no way to tell the secondary transmission unless you know what exactly we're doing and using the right trick to recover it. So we have a lot of ongoing work. We recently demonstrated wideband multi-carrier signal alignment, including lab demonstration. This is currently under review in a journal paper. We are currently working on broadband time frequency hopped signal alignment, because it turns out that by doing repetition in frequency and time, and by doing time frequency hopping, you can actually reap important diversity and secrecy and privacy benefits. We are working on signal alignment with only epsilon rate loss, epsilon being very small. The idea here, I mean, as I presented it in this talk, you gain this beautiful ability to operate under a strong primary interferer, but you do so at 50% rate because of the repetition. Turns out you can do it using other means with very minor rate loss. And we are working on it. We have a number of things coming up. We are also working on coded signal alignment using error control coding, for example, in time and space. We are working on adaptive versions that will bring complexity down to something that is implementable in real time using FPGAs at relatively high rates. We recently got word of an ARL STTR that is in the process of getting started with Nexepta, a small company with expertise in communications engineering, to demonstrate various things relevant to this technology. And at this point, I'd like to acknowledge support from various sponsors. Much of the early part of this work that you saw was supported by NSF, ECCS, and AST. The AST grant is SpectrumX. We're continuing to work with SpectrumX, doing 5G demonstrations of our technology in the powder lab, as well as other developments. The FM lab demo and part of the multi-carrier work was supported by the CCI translation grant, and also by my professorship, the Louis T. Rader professorship work. There is a patent disclosure that we filed, and we're pursuing more disclosures in the pipeline. And that's all I had. I think I made it right on time, and I'd be happy to answer any questions that you may have.